We've seen that spontaneous reactions often have a negative enthalpy. That is, the reaction is accompanied by a decrease in enthalpy. We also learned that spontaneous reactions are accompanied by an increase in entropy. That is, there is increase in randomness where delta S is greater than 0. Thus, we can say that the spontaneity of a reaction involves two thermodynamic properties, enthalpy and entropy. We've learned that entropy helps us measure the degree of randomness or disorder. But, is there a way to predict if a process is going to be spontaneous? In the 1870s, J. Willard Gibbs, an American mathematical physicist, developed the concept of free energy to predict the spontaneity of a process. Today, the term free energy is called as Gibbs energy. Gibbs energy is represented as G and is calculated as free energy. G equals enthalpy of system H minus product of absolute temperature T and the entropy of the system S. Based on the equation, Gibbs energy of a system in initial state, Gi is equal to the enthalpy of the initial state, Hi minus the product of absolute temperature and entropy of the initial state, Tsi. Similarly, Gibbs energy of a system in final state, Gf, is equal to enthalpy of the final state, Hf minus the product of absolute temperature and entropy of the final state, Tsf. Thus, change in Gibbs energy, that is, Gf minus Gi, equals change in enthalpy. Hf minus Hi minus product of absolute temperature T and change in entropy S, Sf minus Si. That is, delta G equals delta H minus T delta S. This equation is known as Gibbs-Helmholtz equation or Gibbs energy equation. Let's see how Gibbs energy is related to spontaneity in irreversible reactions. We know that the total entropy change of a system which is not isolated from the surrounding is calculated as delta S total equals delta S system plus delta S surroundings. Let's consider a system in thermal equilibrium. The temperature of the surrounding will be the same as that of the system. We know that increase in enthalpy of the surrounding is equal to decrease in the enthalpy of the system. Thus, enthalpy change of the surrounding, delta H surrounding divided by temperature T, will be equal to the negative enthalpy change of the system, delta H system divided by temperature T. Thus, the entropy change of the surrounding, delta S surrounding, will be equal to enthalpy change of surrounding divided by temperature, which is equal to minus enthalpy change of system divided by temperature. On substituting the value of delta S surrounding, we get delta S total equals entropy change of system, delta S system plus minus enthalpy change of system, delta H system divided by temperature T. On multiplying both sides with T, we get T delta S total equals T delta S system minus delta H system. But we know that for spontaneous processes, change in entropy delta S is greater than 0. Thus, we can rewrite the equation as T delta S system minus delta H system is greater than 0. Now to write this in terms of Gibbs energy, we need to convert the negative enthalpy change to positive. Thus, we will take out the minus sign and the equation becomes minus into delta H system minus T delta S system is greater than 0. But delta H system minus T delta S system is equal to change in Gibbs energy delta G. Thus, we can say that minus delta G is greater than 0. This means that delta G will be less than 0. Therefore, delta H system minus T delta S system is less than 0. But delta H system minus T delta S system is equal to minus T delta S total, which means that minus T delta S total is less than 0. This means that T delta S total is greater than 0. But when the value of delta S total is greater than 0, it indicates a spontaneous process. This means that change in Gibbs energy less than 0 indicates spontaneous process. Therefore, we can conclude that if at constant temperature and pressure, change in Gibbs energy delta G is negative, that is, less than 0, then the process is spontaneous. Similarly, if delta G is positive, that is, greater than 0, then the process is non-spontaneous. And if delta G is equal to 0, the process is at equilibrium. Now, let's look at Gibbs energy for reversible reactions. We know that during a reversible reaction, a process or reaction can proceed in either direction simultaneously, so that a dynamic equilibrium is set up. Reversible means that the reactions in both the directions should proceed with a decrease in free energy, which seems impossible. This is possible only if, at equilibrium, the free energy of the system is minimum. If it is not minimum, then the system will spontaneously change to the configuration of lower free energy. Thus, the criterion for equilibrium, that is, when A plus B in equilibrium with C plus D, implies that delta Rg is equal to 0. Delta Rg is the Gibbs energy change for the reaction and is equal to the difference in the enthalpy change of reaction, delta Rh, and product of temperature T and entropy change of reaction S. At equilibrium, delta Rg equals 0, which means that at equilibrium, delta Rh equals T delta Rs. If all the reactants and products are in standard state, then delta Rg becomes delta Rg naught. that is, change in Gibbs energy at standard state. This can be expressed as delta Rg equals delta Rg naught plus RT log K, where R is gas constant, T is absolute temperature, and K is the equilibrium constant for the reaction. This can be further expressed as 0 equals delta Rg naught plus RT log K, or delta Rg naught equals minus RT log K, or delta Rg naught equals minus 2.303 RT log K. Therefore, we can conclude that if change in Gibbs energy at standard state, delta Rg naught, is negative, that is, less than 0, then the process is spontaneous. Similarly, if delta Rg naught is positive, that is, greater than 0, then the process is non-spontaneous. And if delta Rg naught is equal to 0, the process is at equilibrium.